Okay. Alright, so we want to find the Laplace of t. Okay, a variable. Alright, so something that changes. Alright, it's not the same as the Laplace of 1 or 4 or whatever, because those were numbers, they were constant. They don't change. They're part of the equation that never changes, they'll always be the same. While t is a variable. T is what changes. It's time. And time changes. So when you record it in an experiment, you record it over some data or whatever, time will change. Okay, it's the variable of your equation. So now that's why it's a bit different and it's complicated. So it's not, the answer is not t over s, because that's not how it works. And I'll show you why that's not how it works. Okay, in fact, it's quite complex, but we'll go on. All right. So, so we say that this should equal, messed up the infinity sign there, e minus st times whatever it is that's here. In this case, it's t, and we integrate it in terms of t. Okay? Alright. Now, the first step is always to integrate what's inside. Well, sorry. Okay, let's say the limit is a goes all the way to infinity, and I'm going to replace infinity with a to make my life easier. And I'm going to rewrite this down. That's a multiplication sign. dt. Okay. Now, the thing here is, this is going to require integration by parts, because this is this is a function with t, and this is its own function with t. So we're going to have to do integration by parts. Now, integration by parts is basically, the rule for it is uv minus the integration of u prime v. Alright, doesn't make sense yet. Alright. Okay, I advise you to watch a video separate to this on integration by parts, okay? But I'll just try to quickly go through it. Alright? So usually you pick something that's, alright, so if I just say differentiation, integration, positive and minus, alright, I'm gonna pick something I can differentiate easily, okay? And well, if I look here, I can differentiate t easily. If I differentiate t, I'll get 1. It's easy. Right? Because if you differentiate t, t to the power of 0, t to the power of 1, 1 minus 1 is 0, t disappears, you're just left with 1. Okay? And if I integrate e to the minus st, I'm just going to get 1 over minus e minus st. Okay? Now, sometimes it's actually easier to integrate to differentiate the e rather than the t. Alright, so sometimes we will be switching this up. Alright, so if you imagine v to be what we've integrated, and differentiation is the u. Okay, you honestly need to watch another video on this. It's just, there's not enough time in the world. Well, no, there is, but you just need to watch another video on this, on the integration by parts. It's not that bad. Loads of people do it. Khan Academy, that Nancy girl, she does it. Loads of other, Easy Math does it. Loads of people do it. I do it too, but I hate it. Not because I just do it all the time. I hate it because it doesn't work for my stuff. Because it's a pain in the backside. Anyway, all right. So when we suss this out, okay, what we're gonna get is when you put these into this order, alright, you'll get t, which is my u, okay, and v, we use this v, alright, it's them two that we're using together at the start for this part here, okay, t times 1 over s e minus st, yep, okay, and, okay, alright, let me just write it down, because this is going to get messy, minus, alright, the integral sign, because that's part of the equation over here, alright, and the integration was to infinity and 0, alright, of minus 1 over s e minus st multiplied by 1. I'll write it. Multiplied by 1. Okay? But now, if you look at this part, okay, this part has no more integration, alright? We've technically, that part is, so this whole thing, this whole line here is the integration of this part, alright? So this part here is integrated to give me this, alright? So technically speaking, this part here needs to have its limits, which is a and 0, alright? I've left this to be infinity on purpose, and you'll see why in a second, okay? So, this part here, okay, if I clean it up slightly, I'm going to get t minus s e minus st. And don't stress, just keep following the video and I'll tell you something funny at the end. Let me just copy this down. Alright, what we can do here, okay, s is just a constant. S is just, well, not a constant, it's just s. S is just s, okay? T is the variable, alright? S is just a constant, okay? It could be a number, 5, 3, 6, 0, whatever, okay? So I can take this negative 1 over s, I can stick it on the outside, alright? 1 over s, and that minus will come with it, it'll turn this into a plus, okay? And what I end up getting is, in this bracket here, I'll get e minus st times 1 is just e minus st, okay? Now there's something cool about this one here, and if you can spot it out, good for you. If you can't, just give me a sec and I'll go through it. If I plug in the limits here, I'll have one bracket with, I'm replacing a with the variable, and the variable here is t, okay? So I get a over s, e minus sa, minus 0 over s, e minus s to the 0, plus 1 over s, infinity, 0, e minus st. And, well, if you remember before, this is stronger than this. Alright, so the exponential rule, because that's going to negative infinity potentially, and that's going to positive infinity, this is just going to give you 0. Alright, this, well, that's going to be 1. Minus s times 0 is just 0. E to the power of 0 is 1. 1 times this, which is 0, is 0. Alright, plus this lovely thing here. Now, 1 over s, we're going to copy it down. Okay. But if you remember what we had at the start, okay, remember, the Laplace of 1, okay, is this. Okay, and we proved that to be 1 over s. If you check the last video, we proved that the Laplace of 1 is this, which equals 1 over s. So I can replace this, hence why I didn't change the integration sign, I can change this into 1 over s. Okay, so this gives me 0 minus 0 is just 0, plus 1 over s times 1 over s, which is 1 over s squared. Alright, so now I'll go up here and I'll write it in a different color. I have just proved that L of t equals 1 over s squared. Now here's the funny thing, okay? Here's the funny part, alright? These are rules. It doesn't matter what the variable is. If this t was f, I'd still get 1 over s squared. If it was k, I'd still get 1 over s. The variable, okay, so it's a rule. Let me for variables, things that change, which is this, okay, the solution we get is 1 over s squared, regardless of what the variable is, okay, as long as it was f or k, it can't be f squared or k squared, as long as if it was f, k, t, just a variable, okay, the variable isn't experiencing any other function, It's not being squared, it's not being times, it's not being divided, it's just the variable, okay? So the solution to just the variable will always be 1 over s squared. And the solution to a constant, so a number, will always be, well, it depends on if it was, for example, L1, it will be 1 over s. If it was L2, it will be 2 over s. L4 will be 4 over s. Are you getting the point? Okay? These are constant rules. You just have to understand them and address them properly. So technically speaking, you can cheat your way in an exam or whatever. You can just look at it and you can say, well, that's 1s squared, that's ls. But of course, you're heavily relying on the fact that the question is going to be straightforward and it's got a variable that's not being played with plus a constant that's just a constant. Okay? But if it's a risk you're willing to take, it's a risk you're willing to take. So the solution, my point is, as long as they're the same sort of thing, the solution will always be the same. The steps will always be the same. It won't differ for anything else. Are you seeing what I'm saying? I hope you are. Okay, so this part, okay, is the last part of this Laplace